All right. Welcome back to the part two. So now that we did a quick review of the previous class, we can now move on to Nystrom. Okay. So Nystrom is a way to approximate the kernel matrix. Now you can imagine that a kernel matrix, the way it works is if you have n samples, then the whole matrix is n by n, therefore it's n squared. Now, if you have one, this implies there's a lot of numbers in this matrix. Right? If you just have 1,000 samples, you're going to have 1,000,000 values to fill. Right? That's just only 1,000. And today we have way more than 1,000 samples. We could have 1,000,000 samples. Then we're going to have 1 trillion numbers to fill. Now, if you have to fill 1 trillion numbers, that's a lot of computation that you have to calculate. So the idea of Nystrom is that essentially they claim that you don't have to calculate this. You can divide the matrix into quadrants where this A is tiny. So if this is 1,000,000, maybe this is 5,000. So this is much, much smaller than 1,000,000, right? Imagine this is million by million matrix. So they're trillion numbers. So this is 5,000. And calculating this, dealing with a 5,000 is much, much easier. Okay. So the claim of Nystrom is that all you really have to calculate is A and B. And since a kernel is a symmetric matrix, you will automatically know this part. Therefore, by using this A and B, you are able to somehow predict the value and approximate the value of C. So you don't need this giant portion, right? Out of 1,000,000, what is 1,000,000 minus 5,000? I mean, that this is a very giant matrix. So that's the idea, right? And the reason why this will work is because if you remember from sampling, that if we have 1,000,000 samples, very often we don't need to use the entire 1,000,000 samples to calculate various statistics about it. If we want to find the average height of 1,000,000 people, chances are you don't need the entire 1,000,000 people. You just need a percentage of it, right? A subset sample, like n hat. You don't need the entire million. And if you just take the average of the subset of the population, it due to the law of large numbers, you are able to essentially approximate the true average. Okay, so that's the general idea. So you can imagine that if we have 1,000,000 samples and we just randomly shuffle them, we randomly shuffle the entire 1,000,000 samples. So x1 is here, x2 is here, x4 is here, right? You randomly when you randomly shuffle them, and you just if you need to construct a matrix, the first portion of that is random samples from the entire million. So this matrix A, in a way, is a subset of the K matrix. It's kind of a snapshot, a summary of A, where you are just randomly sample from the whole population. So you can kind of picture the A matrix is kind of a subset representative of the total matrix K. Okay, so remember, if this is a representative of this, this must hold some kind of information similar to K. And the information we claim that it holds is that if you calculate the eigenfunctions using A, that would be the approximation of the eigenfunctions using K. Okay? So from Rosasco's proposition, we know how to find the eigenfunctions of A from K. Right? So from last lecture, we basically learned that if you know the eigenvectors, you can get the eigenfunctions. So let's say we simply deal with this matrix A here, and we know the eigenvectors. So we take the A, we calculate the eigenvectors, and this phi is the phi A. This is the phi matrix that construct A. Okay, phi A transpose is equal to A. Okay, so that's what the phi A means. So you can imagine we can now take the eigenvalues and eigenvectors and approximate the eigenfunction. So by using A, we are approximating the eigenfunction of K. Now, that's the point. So where and then I want you to keep track the notation. The notation here is E. So this is the eigenfunction approximation, and this is the true eigenfunction if you use the entire K matrix. So if you had you use the entire K matrix, you would get the true one. But by using A, if A is sufficiently large, the approximations should still do a reasonable job. Okay, so keep the notation straight. The eigenfunction, eigenvalue, eigenvector, these are all for K. Okay, this is eigenvalue, for eigenfunction, and these are all from A. So look at the little hat symbol. So all the hats is kind of telling you it came from A. Okay, so let's keep those notations straight. Okay, now that we are able to apply the eigenfunction, so we have an approximate eigenfunction. Remember what Mercer's theorem was telling us. It was telling us that instead of using the regular feature map, we can use the eigenfunctions instead. But we don't need to get the eigenfunctions from K if we already have the eigenfunctions from A, because they're an approximation. So we have the approximate feature map using the eigenfunctions of the matrix A. And when we have these functions, right, they're in RKHS, therefore we can use the reproducing property. And if you remember what the reproducing property was, is that if you have a function, this is equivalent to 5x transpose times f, because the function here is a point in space. We can picture the function, imagine it as a vector, here as well as a vector. Therefore, if we do this, then if it's a function e, then it's simply e, right? So you can kind of picture for this one, e1, it will be written this way. So let's copy this down for every one of them. Eigenfunction 1, eigenfunction 2, all the way to eigenfunction m. So we have all the eigenfunctions. Once you have all the eigenfunctions, notice how phi is the same. So we can pull phi out. So we pull phi out, and here are our approximate eigenfunctions. Now, one quick note. We're approximating the feature map. However, in the process of approximating feature map, these are still we still have the original feature map, right? Of course, we're going to cancel them out later, but I want you to notice the difference between these feature map and these. These are the basis feature map using basis functions. This is the feature map using the approximate eigenfunctions of A. Okay, so that's the difference. So anyways, so now that we have this is equivalent to this. We know how to get the approximate eigenfunctions from the previous page. We just plug this into every one of them, right? If we plug this in, this will be the red portion here. Notice how all I did is plug it in into the first, second, third. And after I plug them in, notice how phi A are all identical. So we can pull phi A out. So phi A out. Once we pull phi A out, notice how we can pull these out too. So the red portion is the red portion here. Take a quick look how if you just multiply this, multiply these, this is equivalent to this notation. Okay. Now, at this point, these are the eigenvectors of A, right? VA, the eigenvectors A. So I'm going to call it V hat right here, and these are the eigenvalues of A, and I'm just going to call it sigma. Okay, sigma hat. So therefore, when I combine all these together, the final result is the approximate feature map is equivalent to phi A, right? Phi A, and then the eigenvectors and eigenvalues, these two. So this right here is equivalent to phi hat of x. This is the approximation using A, using just the A matrix. Now remember, the way you can see this is that this is equivalent to, if you use the reproducing property, this is equal to phi transpose phi hat, right? So that's a reproducing property. So this is equivalent to this part. So phi hat, all we did is we found the representation of what phi hat is, which is the feature map approximated from A. Okay, so this right here is a phi hat. So this is how you would essentially pass the data in and get its features in the feature map. Now, if you only have one sample, this is it. But we want to find the phi matrix. So we have to pass every sample in. So we want to pass every single sample in. When we try to pass every single sample in, then it's equivalent to this right here for x1, then 5x1. So you basically do 5 2 transpose 5 a transpose v hat sigma hat. You can see how when we try to pass every single sample in, you'll result in this. And since this is constant, we can pull it out. As a result, this part right here times this is this part, is how we would be able to get every single sample. This right here, you may recognize this is a phi matrix. Therefore, this should have an A here. Therefore, you have phi times phi A times v hat times sigma. So this right here is equivalent to phi hat. And I'm going to call this simply as Ka. Now, I use Ka because, well, you may remember from the LDA, that's essentially this portion of the kernel matrix. Okay? And now we have phi hat. All you have to do, you have an expression for phi hat. You just have to calculate phi hat times phi hat, which results in this, and your problem is solved. So this right here allows you to calculate. So this phi hat is for the entire kernel matrix. So even though we use the feature map, the feature map came from essentially the A matrix, we're able to get the phi hat of the K matrix. And therefore, this will give you the entire K matrix, even though you got everything only from the A. Okay. Now let's take a closer look. So the Ka matrix, remember, it was equivalent to phi times phi A, right? So what is phi? Phi is, well, if you just pass the feature map through every sample. So that's phi. What about phi A? Well, phi A is it's only this part, right? So if this is the total length n, phi a is much, much smaller. So it's from 1 all the way to n hat, or n a. You can imagine this is much smaller. And when you actually multiply them together, right, this multiply, you form the kernels, the kernel function. So this right here is equal to the kernel function, right? And the size of this kernel, so after you do this multiplication, you're going to end up with n and na, right? And this right here is essentially this portion, which we call a Ka. I call it Ka because we've done this in the previous lecture. In normal Nystrom lecture, they call this portion, instead of Ka, they call it L, which is the same thing, right? They call this L. So that's how we come up to the conclusion. In most Nystrom literature, it's L times the eigen vectors of A and eigenvalues of A. Okay. So that right there is essentially the Nystrom algorithm to approximate the large. And now I wrote the code for you guys as well. Notice how this is essentially the phi matrix we talked about. And you can see that it does a pretty good job of approximating it. Okay, so that concludes part 2. Next, we're going to talk more about Nystrom in part 3.